Okay, so I do want to revisit the emphasis that I made on reactive intermediates, highlighted here in blue. So radicals are reactive intermediates. Other reactive intermediates are anions, cations, okay? We're mostly worried about carbocations when it comes to cations, but obviously we've been talking lots about different kinds of anions: oxygen, nitrogen, carbon, sulfur. Okay, these are all reactive intermediates. Why is the word intermediate important? It's important because you need to understand what an intermediate looks like on an energy diagram. Okay, so yes, radicals are intermediates. So here we have a blank reaction coordinate, and we have our halogenation steps shown here with the enthalpy changes for each step. All right, so what I want to do is just remind you of what a reaction coordinate is. A reaction coordinate has energy on the y-axis here. It has reaction progress on the x-axis down here. Remember, the start of the reaction is always on the left, and the end of the reaction is on the right. Always, always, always. Okay? And the things that you should be able to recognize on a reaction coordinate is where the starting materials are, where the products are. You should be able to identify an activation energy. You should know where the transition states are, and you should know where the intermediates lie. Okay, intermediates is tough because intermediate, when you hear reactive intermediate, you think high energy. Okay, and they are high energy compared to starting materials and products. Okay, however, transition states are higher in energy. Okay, reactive intermediates, intermediate means that it hangs out long enough to be observed by some of the techniques that we have available as scientists. Transition states are such high energy that we can't even detect them. Okay, we have to just guess what they look like. Okay. Okay, so now what I'm going to do is I'm going to try to freehand a reaction coordinate for this reaction, okay, using our 4 steps. So we start off with all of our reagents in a flask. All right, so it's in the dark, nothing has happened yet, there's no reaction. All right, so the energy level of all that, I'm just going to pick an arbitrary level right there. That is our starting point. And the first step of the reaction, we're going to expose this to blue light, which is energy. Okay, and this does an endothermic process of cleaving molecular chlorine into the 2 chlorine radicals. All right, and so from start to finish here, we are putting in 57 kilocalories per mole. So I'm going to highlight that energy level up here. Okay, so the energy difference between that red line and the orange line, I'm indicating on the y-axis here. Okay, so that energy difference is 57 kilocalories per mole. And it's gone up in energy, so again, it's endothermic. Okay, so the next step, from there, we have a chlorine radical that reacts with methane to give us a methyl radical and HCl. All right, and this process, from start to finish, takes 2 kilocalories per mole. All right, so it's still endothermic. We're still going up in energy, so I'm going to make this energy level just a bit higher than our red energy level. All right, so what happens next? What happens next is the methyl radical forms chloromethane and another chlorine radical in what is now finally a step that's giving us energy back. So this is finally an exothermic process. Okay, but it's only giving us 27 kilocalories per mole back, so it's almost half of the 57, so I'm just going to ballpark this again. And I'm just going to make that a 27 kilocal per mole drop from the blue to the green. So again, on our y-axis, that is approximately 27 kilocalories per mole. And then finally, with all of these reactive species hanging out, we do have a chlorine radical from our first step, a chlorine radical from our first step, and a chlorine radical from our second to last step, which can combine to give us Cl2. Okay, this is an exothermic reaction that gives off 57. All right, so again, I'm going to try to make this the same energy gap as between the red and the orange levels, but now going down from the green to the purple level. Okay, so here are our 5 energy levels where we can recognize what we have. All right, so, hold on, I'm switching colors. All right, so this is our starting material. Okay, this is, everything's all said and done, we have our products. All right, so what do the other energy levels represent? Do they represent transition states or intermediates or activation energies? Okay, well, hopefully you all went, oh, it's intermediates because radicals are intermediates. Yes, they are reactive, they are high energy, but they are intermediates, okay? So remember, intermediates are always local minima on graphs, okay? So they're the lowest point on, a trough of a curve, okay? So when we actually draw the reaction pathway, energy profile of the entire reaction, okay, this doesn't look like this, right? This should not look like a reaction coordinate to you guys, all right? What it's going to look like is something like this. And again, I'm freehanding this, so it's not particularly good, but it will suffice. Okay, so here we have our reaction coordinate. All right, so at the top of each one of these curves, so there, 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 and there. At the top of all of these hills are the transition states. Okay, TSs, transition states. Okay, these are local maxima, right? They're at the top of these hills, all right? So these transition states are so high in energy that they can't be detected, okay? They don't hang around long enough to be detected, okay? However, all of the intermediates do. So this, and this are intermediates. Okay, so the last thing I want to point out, I'm running out of colors, but the last thing I want to point out is that this value, okay, so from the top of that hill to the energy level from whence we started, right? So this vertical line represents activation energy, okay? So this is the energy of that blue light that cleaves the chlorine-chlorine bond homolytically into the two radicals, okay? So this dark green line, this vertical line, represents the difference in energy between our starting energy level and the top of that hill. Okay, that energy difference is the activation energy. All right, once that happens, the rest of this reaction cascades. Okay, so this should all be review from Gen Chem, but I wanted to walk you through it anyway. I hope it's clear. If not, I'll be happy to talk about this in office hours. And we have a few more things to talk about in terms of radical stability and how that affects halogenation of more complex hydrocarbons besides methane, but we'll talk about that a little bit later. All right, so any questions, feel free to email me or stop by my office and we will talk about whatever you like. Thanks very much.